Welcome everyone for this webinar series for the autumn. And we shall start this webinar series with Professor Romain Fleury from École Polytechnique Fédérale Lausanne. And Romain is going to talk on topological metamaterials for robust signal and energy manipulation. Please, Romain.
So thank you very much, Sébastien. I want to thank all the organizers for giving me the opportunity to present here some results that we had recently with the group that I'm leading at EPFL. And I know that there has been some talks already on topology in this seminar series, and this talk is intended to be a little bit different. So in my group, we work on different types of activities. We have activities, long-time activities in active and non-emission acoustics. More recently, we are doing some imaging, and we also had some activities and still have some activities in topological metamaterials, and that's the topic of this seminar. So this is the outline for today. I will give an introduction, a low-level introduction to what is topology, the concept of topological invariants, and why do we care about this in wave physics and wave engineering, and giving a few examples to better understand the rest of the talk. And after doing that, we will talk about topological scattering, meaning that we send waves and they scatter by exciting a topological mode. So we'll see how this can be applied to make filters and explore in what sense these filters are robust to geometrical imperfections or other kind of imperfections. So we'll see what we can do there. And in a third part, I will talk about how to manage energy, focus energy, or concentrate energy using topological properties. So let's start with the first introduction, the first part. So what is topology? Topology is initially a branch of mathematics that studies continuous transformations of mathematical systems. So you have to pick a system, for instance, a closed surface as an object of study for topology. And topology basically asks the question, if I do continuous transformation on that object, what kind of class of object do I get? So from the standpoint of topology, a sphere is just the same as a spoon. These are topologically equivalent because you can deform this sphere into the spoon in a continuous way. The sphere, however, is distinct from something else like a torus, because you cannot deform the sphere into the torus without a discontinuous transformation, which would be creating a hole. The torus is the same family as the teacup. And the third family is the double torus. Double torus is distinct both from the sphere and the torus. It's the same family as this tea jar. So topology is about classifying these objects. And we often deal with topological invariants, which are integer numbers that describe each of these class of objects. So this class has 0 hole, so we can count the number of hole or handles in those closed surfaces, and this is called a genus. It's an integer number that classifies those objects. So for this is 0, for this is 1 hole, 2 holes, etc. So this topological invariant, the genus, are integer numbers, and there are often many ways to define them. So for instance, if you take again a sphere and you try to define on it a continuous vector map, so you try to put some vectors in a continuous way on the sphere, you will see that you will have to create at least 2 vortices, meaning something like that, like a point on Earth with no wind. So there's at least 2 of them on each continuous vector map on a sphere. And this, the number of vortices, the minimal number of vortices you have to create to cover the sphere, is dependent on the topology of this sphere. If you take a different shape, like the donut, then you don't have to create any vortex. And it turns out that the minimal number of vortices of a closed surface is related to the genus, the number of holes. There is a formula that links both of them. So often you will see this in topology. You often have very different ways to describe the same thing, to calculate topological invariants. So why do we care about these mathematics in physics? So is it sometimes relevant to define topological properties for physical systems? I will show you here a very simple example that is useful to have in mind, because we will use it for understanding the topology of waves. So let's consider we first have to pick a system, and the system that I pick, the class of system that I pick is a set of two objects that are conductors, metallic conductors, in electrostatic equilibrium. So I have two of these objects, and that's my system, the pair of them. Can I define topological invariants? Well, we know that they can carry charges. So for instance, this one has a plus E charge, and this one has two negative E charge. So I can count the number of charges on each of these objects and say, okay, that's my topological invariance. So are these good topological invariants? They are integer numbers, that's clear. Can they change upon continuous transformation of this object? Well, I can modify the shape of this pair of objects as long as it remains a pair of objects. The number of charge don't change. So they are good topological invariants. They can only change if we go through a discontinuous transformation of this pair of objects in which it's no longer a pair of objects. So if they touch each other at some point, then they can exchange the electrical charges and the invariant can change. It's only with this discontinuous transformation. So this is really the nature of topological invariants. So, of course, this is a very simple example, but I will show you in a minute that the bands in a band structure of a periodic material, they behave just in the same way. So how does it play out in periodic structures for waves? So if we have waves in periodic structure, we know that we can define a band structure. This is just a schematic example. So whether it's 1D, 2D, 3D, whatever, we have a set of bands. And the first thing we are going to assume is that the bands are separated. So there are some band gaps. Okay, so this is an insulator. And we are going to be able to define things that just behave like charges on this band structure. So you have to imagine that they carry one charge of positive or negative value, or two charges, or a certain number of charges. And these charges cannot change if I continuously change my system. So I move around my atom in my metamaterial. As long as two bands do not touch, they keep the charge. So it is only by going through a discontinuous transformation of the band structure, where some band gaps close, that they can exchange those charges and change the topological invariant. This is extremely important to keep in mind. It's just the same as the electrostatic equilibrium between two conductors. So why do we care about defining those charges? I will tell you later how to define those charges, but so far, let's imagine that we can define them as charges. Why do we care about this? Well, we care about this because we have special behavior on the edges of those systems. So imagine that I have a situation where I have two systems, wave systems with different topologies. First topology, second topology. What does it mean? It means that they have band structures, but the bands carry different charges. Okay? And I asked the question, what is going to happen at the interface? Because here I have a set of bands with given charges, but these charges cannot change from these values to these different values. So what happens at the interface? Notice that here I assume that the band gaps overlap in the same frequency range. So, in fact, since this number cannot change from 1 to 0 without closing the band gap, then I am completely sure that at the interface somewhere, the band gap has to close. So something like that has to happen. But if something like that happens, it means that I have a state here that is surrounded on the right by a band gap and on the left by a band gap. So it means that I have an interface state. I can have, for instance, two of them, one in one way, one in the other way. And these interface states, they don't depend on the shape or what is at the interface. They just depend on those charges. In other words, properties of the bulk. So it is the topological property of the bulk that guarantees the existence of these interface states. All right, so if I summarize what I said so far, topological insulators are very much like everyday objects that we find every day in Switzerland that are chocolate bars. So why? Because if you look at a chocolate bar, you open the box, you see that the inside is an insulator. There is no possible propagation. It's the band gap that separates the bands. But on the boundary, there is always an edge state, so the possibility to have conduction, electronic conduction on the boundary. And they are very special chocolate bars because if you break this chocolate bar into two halves, then you never get to the chocolate because you create another interface with air, and then you need to have interface states. All right, so far I have explained to you what is a topological invariant on a band structure. So it's like a charge associated to each band, and it has consequences, the existence of edge modes, but I haven't told you how to define that charge. And in fact, as I showed you in the beginning of the talk, there's often many ways to define a given topological invariant. So I show you one example here that I think is the simplest because it's a one-dimensional example. And it's known as the Su-Schrieffer-Heeger chain, SSH. And it's basically a very simple system. It's a chain of coupled oscillators with the same resonant frequency omega 0. So there's omega 0 everywhere, and they are coupled to each other by coupling constants that alternate between two values, a first value k and a second value j, and then it repeats itself. And this has topological properties, and I want to show you how the charges are defined in this case, because this is going to be important for the rest of the talk. All right, so we can define a unit cell, and we can write coupled harmonic oscillator equations and Bloch theorem, and we calculate something called the tight binding Hamiltonian of the chain, which is a Hermitian matrix that I just wrote for you here. It depends on KB, which is the Bloch wave number, this value, and it describes basically how the two resonators in the unit cell are coupled depending on the labeling from the Bloch theorem, the Bloch wave number. So if we look at this chain, we can just physically, without doing some topology, we can identify two different regimes. We see that this chain is basically some dimers, omega 0 coupled by k, and these dimers are coupled together with j. So there's two regimes. The first one we are going to look at is the weakly coupled dimers regime. So you have dimers, and they are coupled to each other with small coupling coefficients. So this j has a smaller value than k. If you look at the band diagram, and you can get to this band diagram by taking the eigenvalue of that matrix that I just showed here, you see two bands because it's a 2 by 2 matrix. And you can look at what are the modes on one band. Say I pick this band, the blue one. I can look at what is the mode there. And if I look at the mode, I see that it's pretty much a monopole everywhere on the band. In particular, at the center of the Brillouin zone is a pure monopole, and at the edge is a pure monopole. That's for the blue band. The other band is also a pure mode. It's a pure dipole more or less a pure dipole everywhere. So that's the first regime, weakly coupled dimers. Now let's go to strongly coupled dimers. And we see something completely different. You also have two bands, and if we look at the symmetry of the mode along one of the bands, we see that this symmetry is totally different across the band. For instance, in the center of the Brillouin zone, it's a pure monopole, And when you get to the edge, it becomes a pure dipole. And you have everything in between across the band. So there is a complete difference, at least physically, between the strongly coupled dimers and the weakly coupled dimers. In one case, you have a maintained mode symmetry across the band. And in this case, you have a mix between mode symmetries. So there's something different. So we want to say that probably there is a difference in topology. But to claim that, we need to define a topological invariant. So just before I do that, there's a few things to keep in mind to understand very well how this is done. The first thing is the Bloch wave number. It's a number that lives on a circle. Why? Because it goes from minus pi over a to pi over a, but this pi over a and plus minus pi over a, they are basically the same mode. So you can wrap it up on a circle. That's the first thing to remember. The second thing is the Hamiltonian. It lives on a space of 2 by 2 matrices, but they have a special property because they are Hermitian. And if they are Hermitian, we can always expand them on a basis that is well known, and it's a basis of Pauli matrices. So you have the sigma x, sigma y, sigma z, and you have some components for the Hamiltonian, dx along sigma x, dy and dz, and these components depend on k block. So when k block goes around a circle, this matrix go around a closed path in this space of 2 by 2 Hermitian matrices. If you want to represent this, you can plot this closed path in the dx, dy, dz space, and we know that as k block goes through the circle, we go through some kind of closed path. This is the vector d of kb in that space. Okay, the third thing that is going to be important is the fact that the eigenvalues of the Hamiltonian give the two frequency bands. So if I look at this form, I can easily calculate the eigenvalues from this, and I find that there are two eigenvalues. This d0 coefficient times the identity is basically an offset, it doesn't really matter for the physics, plus minus the norm of that vector d of k block. So for instance, this is important. Why? Because we see that in order to have a closed band gap, the norm of d has to vanish at a specific value of k block. So it means that, and that's a very important property for the topology, the band gap closes when I find a value of the wave number that cancels this d, the norm of this vector d. It means that at some value of k block, I go to the center, to the origin of that space. So my closed contour in my space of matrices goes through the origin. Okay, so we have a few things to keep in mind, and now we are ready to define the topology. So we start from the Hamiltonian, and the first thing we do is we notice that in the case of the SSH chain, because we have identical resonators, it's omega 0, omega 0, omega 0 everywhere, then there is no dz term. This is always 0. And this is known in condensed matter theory as chiral symmetry. This is an important condition to define the topology. If you don't have that, you are not able to do it. Okay. So then we can calculate those functions. It's very easy from the Hamiltonian. We find that those simple expressions, and we see that the path that we follow in the dx, dy plane as k block go through the Brillouin zone is another circle. It's just a circle in the dx, dy plane. Okay. So now we are ready to look at what happens in our two regimes. So let's look at this. This is the weakly coupled dimer regime. So we didn't have any symmetry inversion on the band. What happens here? Well, the circle in the space of matrices of 2 by 2 Hermitian matrices in the dx, dy plane is like this. Okay. So now let's look at the other regime, the strongly coupled dimers, the one that had a symmetry inversion. Now our circle is like this. If you look closely, there is something fundamentally different between those two situations, because this circle encircles the origin here, whereas this one does not. So we can characterize this difference by computing the winding number of that circle. Basically, does it encircle the origin? No, then it's 0. And here, if it encircles the origin once, then the winding is 1. So we want to propose this winding number as a topological invariant. Is it a good topological invariant? So I have to go back to the definition of a topological invariant. It has to be an integer number. This is good. But it also needs to be, it can change only if we go through a discontinuous transformation of the band structure. So let's look at the intermediate case when it changes. When k equals j, it changes, we see the transition circle, it touches the origin. And I just said before that when this closed path touches the origin, it means the band gap closes. So indeed, this number only changes when it crosses the 0 here, meaning we have a discontinuous transformation of the band structure, the band gap that closes. So this is a good topological invariant. Okay, I did mention that this, what I call chiral symmetry, the fact that dz, the third component of the Hamiltonian along the sigma z matrix, is equal to 0, this is chiral symmetry, is a very important condition. So let's see what happens. Why is it very important? So let's imagine you have a system where you have dz equals 0 everywhere. It means that to go from a winding number equal to 1, which is this situation, to a winding number equal to 0, since dz is always 0, I'm on that dx dy plane, so my circle has to slide on that plane, and necessarily to go from there to there, my circle has to cross the origin. There's no way around it. And when my circle crosses the origin, I close the band gap. So it means that if I connect a system with winding equal to 1 to a winding equals 0 and dz is 0 everywhere, then necessarily in the middle, since I'm sliding this circle, I have to close the band gap. So I need to have an edge mode. However, when I have broken chiral symmetry, dz is non-zero, can be non-zero. So I can go from a winding number equal to 1 to a winding number equal to 0 by just lifting that circle. And then if I lift that circle, I don't need to cross this point anymore. So I don't need to close the band gap. So if I connect a system with winding equal 1 here far from the interface and winding equals 0 here, by an interface in which dz or the chiral symmetry is broken, like this, for instance, well, maybe this function of d of x, dz of x, can lift this circle and prevent the edge mode to appear. So I don't have necessarily an edge mode. So this is very important. We have edge modes that are protected by this special chiral symmetry. So what's the physical consequence of this? Let's look at this. I propose to look at a system like this. You have two finite systems, let's say 4 resonators. These ones have a winding. If they were infinite, this would describe a Bloch Hamiltonian having a winding of 1. And this one has a winding of 0. So now what I'm going to do, these are just 4 resonators on each side of this interface. I'm going to excite it from the outside. So we have to imagine that there is a waveguide here coming. And I send a wave in this waveguide, and there is some kind of coupling constant to the first resonator. I can reflect waves, or maybe it can go through the chain and be transmitted here to another waveguide. And what I'm going to do is I'm going to look at the transmission to this other waveguide as a function of frequency. This is this plot. If I do that, I recognize several things. So I have here, sometimes I can transmit, this is a bulk through the bulk band, the first bulk band, then I have a band gap, and I have a second bulk band. But in the middle of the band gap, I see a peak. And this peak corresponds to resonant tunneling from here to there through the interface state that is here. Okay, and I see that it's inside the band gap. Okay, good. This is a perfect situation because this has no disorder. Now let me put some disorder, but I preserve the chiral symmetry. So I'm always guaranteed to have that edge mode, even if I have disorder. So I put some disorder on the couplings. So this has random disorder. And basically what I'm doing in this plot is I'm focusing on the band gap. So what the red thing you see is this peak in the middle of the band gap. And I increase the disorder strength. And I do some average of the spectrum of this peak over disorder realizations. Something like 50 disorder realizations. And what I see is that this peak survives. It survives even very high values of disorder. So that's because chiral symmetry is preserved, and so I must have an edge mode in all cases, as long as I don't destroy my topology. Now, if I break chiral symmetry, it means that I must not have identical resonators. This shouldn't be omega 0, omega 0, omega 0. Say A, B, C, D, E, F, G. I put some disorder here on the resonance frequency. The picture is totally different. You see that the transmission peak goes all over the place and I don't have robustness. There is even some realizations of disorder where I don't even have a peak in the band gap. All right, so this was an introduction to explain what topology is in general, and we have seen a few properties of topological wave insulators, like the presence of edge states that are symmetry protected. Now we want to use this to create or to explore whether we can create some interesting devices, like robust filters. So I want to do some topological scattering. Why do I want to do this? The thing is, if often in photonics or even in wave engineering, when you build a device, like a photonic crystal or metamaterial, very often you have geometrical tolerances, and what you build is not exactly what you wanted. So there is a difference between what you wanted, what you intended to build, and the actual system you get. And you can have disorder-induced scattering that basically you want here. It's an example of a waveguide. It destroys what you want to do. Here, it kills the transmission because the disorder induces backscattering. So we don't want that. We want to explore whether topology can help in this situation. So we have seen how to build a one-dimensional topological insulators out of coupled resonators. But more often, in the field of metamaterials or photonic crystals, we have these situations where we have multiple scattering. We have a medium that supports wave propagation, and this wave scatters multiply on different scatterers, whether they are resonant for metamaterials or non-resonant for photonic crystals. It's very different from this situation that they have in condensed matter physics, where we have resonances and there's no propagation of wave in between. The wave is evanescent, and this leads to the coupling constant. And we know how to deal with this system, but not yet how to deal with this one. So the way we did it is we look at this Hermitian eigenvalue problem. I just summarized what we just saw. We have a matrix that's Hermitian, and the topology is defined from the mapping between the Brillouin circle and the space of Hermitian matrices, dx sigma x plus dy sigma y, and we saw that the topology is defined by the winding number of d of k. This we know very well. But the problem is, in this case, we don't have that. The eigenvalue problem is this one. M cell is the transfer matrix of the unit cell, and it's basically the Bloch phase times the state. The thing is, you see that it's different from here because, first of all, omega is not the eigenvalue. Now it's K Bloch that is the eigenvalue, and omega is in that matrix. That this can be because it's resonant, because of scattering, everything. This matrix depends on omega. And this transfer matrix there's no reason for it to be Hermitian. In fact, it's non-Hermitian, and it always belongs to SU11 because for systems that obey time reversal symmetry. So it has this form. It's not Hermitian, but it's a different topology problem. However, we can still expand that matrix on Pauli matrices and try to play the same game. We just need to introduce this I number, imaginary number. And we know that we are going to have to define the topology from the mapping between the Brillouin circle and the space of SU11 matrices of the following form. We can show that this coefficient doesn't matter, and it's shown in this paper if you want details. So let's see how to define the topology. So I'm doing the same thing as before. I think that this system where the two scatterers are close to each other is going to be topologically different from this system. That's my intuition. So let's look at the difference between these two. And let's also look at the boundary case, what will be the phase transition case. So I have a system of bands. In fact, I have an infinite number of bands. So I have to pick a band. I pick this blue band here, and I'm going to go through the band with K block and look at how this transfer matrix evolves in the space of SU11 matrices. And I get a completely different picture. There's no circle. It's not a winding number. It's totally different. So as I go from through the Brillouin zone along the band, I start on a cone here at the edge of the Brillouin zone. And then at the center of the Brillouin zone, I'm on the middle. I'm again on the cone. And to go to the other edge of the Brillouin zone, I come back. So I go back and forth on something that is not a closed path, it's just a segment. But it's inside the cone. You can show that it has to be inside the cone and start on the cone and finish on the cone. Okay. Now, I look at this topological case and I see something similar. I start on the cone. I go on the cone at the center of the Brillouin zone, and then I come back to go to the other edge of the Brillouin zone. The difference between the two is that this one crosses the axis of the cone. In the boundary case, my segment touches the tip of the cone. So I can conjecture that maybe the topological invariant is the number of times that I cross the axis of the cone. So I make this proposal. Invariant is the number of times the segment crosses the z-axis. So it's 0 here, it's 1 there. Is it a good topological invariant? The answer is, first, it's an integer number that I can define for each band. And it can only change at the tip of the cone when the band gap closes. Is that true? You can show that it is true at a condition only if and only if the square of the transfer matrix of the unit cell is 1. And this implies directly that the two scatterers, my two disks in my unit cell, have the same individual scattering matrix. So they are the same. So we have the same symmetry protected behavior as in the tight binding SSH, except that we generalized it to a multiple scattering system that can be useful for metamaterials or for photonic crystals, because you can have dispersive elements and everything you want. So let's look at this in order to make some kind of filter. So I take a finite system and I excite it from the left. This is a waveguide. There's a finite number of scatterers and they have a different topology. And here I focus only in the frequency range of the band gap, and I see a Laurentian peak, which is basically the resonant tunneling through the edge mode at the interface. Okay? And this is a case of no disorder. Now I put position disorder. So I move them around and I do some average of this peak over disorder realizations at different disorder strengths. And what I get is very similar as in the SSH. So I get a transmission peak that seems to be robust with respect to disorder. So now let's try another type of disorder. If I change the shape of my scatterers, so ready disorder, now it's no longer robust. Why? Because I changed the fact that the two scatterers within a unit cell have the same S matrix. But wait a second here. Why can I say that when I shift them, they have the same S matrix? So is it consistent with the theory? We check this. Of course, if you move the cylinder horizontally, it has the same S matrix. That's clear. But if you move it up, it's not so clear. Well, it just happens that we are working in a frequency range where if you move this guy up, you don't change the S matrix, neither the amplitude or phase of the S parameters, and we check this numerically. So this is consistent with the theory, that we need to have this symmetry protection. So now we're ready to make filters. So just as a reference case, I start with a trivial filter. So a filter that is not based on topology. So I want to filter a time signal, like a train of pulses like this, with a Lorentzian transfer function. I can do this by putting some scatterers and creating this Lorentzian by including a Bragg defect here. So this is a Bragg crystal and I have a defect. So I can tunnel through this defect and have a resonance peak. And of course, if everything is perfectly ordered, what I get is what I expect. I filter my signal. However, and that's the problem I want to tackle in the first place, if I slightly shift, even slightly, those cylinders, I completely destroy my transfer function, and of course my output is not what I want to do. So let's see if the same thing happens or not with topological filters. So what I'm doing here is I say, okay, forget about the Bragg arrangement. Let's arrange differently those scatterers. Let's create a crystal here with a bulk invariant of 0 and 1 here. So I have a topological boundary in the middle. And let's send the same signal and design this thing so that I have my Lorentzian. Of course, I still get my response. But the difference is that if I put disorder of the same amount with the same strength as before, my transfer function remains because the edge mode is pinned to the center of the band gap, and its existence is topologically guaranteed. So what I did is something a little bit like what happens on that bridge. This is a bridge that was proposed to connect mainland China to Hong Kong. And the problem they had is that in Hong Kong, you drive on the left side of the road. In China, you drive on the right side of the road. So the highways, they don't have the same topology. So if you want to connect them, you necessarily need to separate the two sides and then have a crossing. So you have a left-hand drive country and a right-hand drive country, different topologies of the highway. You have to create a crossing. It's a little bit like what we do here. We have two different topology. We have to create an edge mode. And it doesn't matter that here there is disorder or that the highway takes a tortuous path. It's the topology that counts for the existence of that crossing. Okay, we have validated this in experiment. So we have seen this protected behavior in the case of a topological filter, and this non-protected behavior in the case of a Bragg filter with the same amount of disorder imparted to the position of those cylinders. All right, so far I have shown you how this can be used to make filters that are robust. The question is, okay, this is only for Lorentzian type of line shape. Can you do something a bit more complex? So we have shown that yes, you can have, for instance, a 0 in your filtering response. You can do something like a Fano resonance. So what is a Fano resonance? A Fano resonance is a special line shape, resonant line shape that occurs when you have two modes that interact, but they have a different line width. One of them has a large line width and one of them has a narrow line width. If they interact, you can get a Fano resonance. But the thing is that these things are usually quite sensitive to the geometry of your device. And if you have some imperfections, very often what you get is not what you intended. You can have a distortion of the spectrum or the appearance of new peaks and new modes in the picture. What we want to propose here is, what about we do the same, but we use the interaction between two modes that are topological in the first place. So their existence is guaranteed and they are pinned to a certain frequency by topology. Then if you put disorder, there cannot be a new mode because the number of modes is guaranteed by topology and it cannot disappear. So the only thing that disorder might change is just the interaction coupling between those two modes, but the line shape itself, the fact that it is a Fano resonance, must remain. So let's see how to do that with the same system. So we need a second mode. What we can use is something called bound state in the continuum. This is when you have a cylinder in a pipe, in acoustic pipe, you have a mode that is localized to the cylinder that has an odd distribution with respect to the center line of the waveguide. And this mode is interesting because it's dark. It's dark because it cannot easily couple to the plane wave, the fundamental mode of the waveguide. So it doesn't couple to that plane wave. It's called a bound state in the continuum. We want to use those modes to create the Fano. How can we do that? So let's consider first what happens when you have a periodic array of such rods. So that's my unit cell, and I just look at the band structure. I have two kinds of bands, the blue and the red. The blue is my usual Bragg band, okay? It corresponds to even modes that are created by multiple scattering. This is what I just showed just before in this talk. And there is a new band, another one that we didn't pay attention to, which is this red band. And this red band corresponds to a band created by these guys. Why? Because each of these cylinders has one dipolar resonance, and they are coupled to each other evanescently. So here we have a tight binding kind of interaction for these modes. That's why you have a cosine kind of shape. So now let's change the lattice constant. If we change it a little bit, so these guys are closer, of course we lift up the Bragg bands. But also this red band gains some dispersion. Why? Because these guys are closer to each other, so the hopping is easier between two odd modes, and we have higher group velocity. If we do this further, we can get to a regime where the second blue band overlaps very well with the first red band. And that's what we want. We want two modes overlapping, two bands overlapping in the same range. Now we are ready, so I move to the next slide. We are ready to build a topological crystal out of these two. What we can do basically is we consider two scatterers in a unit cell, we look at the band structure, and we see that these red bands, they have a band gap that is inside the band gap of the blue bands. And this nested band gap configuration is exactly what we want because we want the edge modes to be at the same frequency. Okay? And of course, this setup has a different topology than this. We can check this. So if we do an interface now between two crystals with opposite topology, we are going to have two interface states. We have one that is even, that's the bright edge mode, this one, and we have an odd edge mode, that is this one, built from these individual BIC resonances. And these are completely orthogonal to each other. It's like two subspaces, they don't talk to each other. But for having a Fano resonance, we need them to talk to each other. We need them to be a little bit coupled. So what we are going to do is we are going to shift up this little, all the scatterers from the center line of the waveguide just a little bit to enable coupling between these two modes. And now what we get if we do a scattering experiment on a system with two different topology and an interface in the middle, we get a Fano resonance. We get this blue line shape that is exactly the asymmetric peak and dip, very sharp spectrum of the Fano. So now let's see if we put disorder, what happens. If we put disorder, we see that because the two modes are guaranteed by topology and they are pinned to a certain frequency, the Fano has to remain. But the Fano changes a little bit because the disorder changes their coupling. Okay, so the shape is still sensitive to the outside world, so the Fano can still be used for sensing, for instance. This is interesting. That's what happens when I increase continuously a level of disorder. So I see that I always have a Fano resonance. It's very different from a Bragg kind of Fano resonance that I make using a defect where, okay, I have this Fano when everything is perfect, but when I put disorder, it goes away. And here I put the same amount of disorder as in the topological case, which is 10% of the lattice constant. and this is what happens continuously. So we see that the modes, they go away from the frequency range. We have done experiments to validate this. So this, of course, in experiments you have losses, so this is much less sharp, especially in acoustics at that type of frequency. But we do see a topological Fano that fits with simulation. And when we put some disorder, so we move those guys around, still there. If you do the reference case with a Bragg defect, we can create a trivial Fano, but when we put the same amount of disorder as before, we have a new zero in the picture, so this is completely a different line shape. So we have worked on translating this to other examples because the recipe is easy to transpose. This is I won't go to detail here, but you can look at these papers. This is something for elastic waves. And this example is in optomechanics. It's still under review. All right. So let's think a little bit about what we've done. It's a little bit puzzling because when we have a perfect system, we want to do a given transfer function. We have a relation between input and output. And intuitively, we would say there's only one set of rods that would give me that transfer function to give me this output. Well, what topology shows is that it's not the case. You can have many randomly chosen geometries that give you the same transfer function. And that's interesting because you can say, oh, then I can have randomly picked geometries that perform a definite operation. So can I do can I go even further than this and ask the following question? Can random disorder, so a randomly chosen geometry, induce a definite filtering operation? Induce it. So I don't have it if I don't have disorder, and then I have it because I put some disorder in my system and some randomly chosen disorder. This would be very interesting for self-assembled systems. So the key is to consider something called a Topological Anderson insulator. And there is a very simple instance of them in 1D. You take the same chain as before, couple resonators, all the resonators are the same, AAA as resonance frequency, and you put it in what I call the trivial regime, where there's no edge mode for that chain. So it's weakly coupled dimers. You have strong coupling here and weaker coupling there. And what you're going, so there's no edge mode, there's no way to use this as a filter, there's just no Lorentzian response. But what you're going to do is you're going to add disorder to this. So I multiply these hoppings here by these factors. So what are those numbers? W here is a site-dependent random number. So for each site of the lattice here, I'm changing the coupling by a random number, and I take this value between -1 and 1. And ds is just quantifies the strength of the disorder. Notice that I'm not playing any trick here. I'm not trying to, on average, go to a non-trivial chain where this would be higher than J, because this W is chosen between -1 and 1. So on average, my system is still trivial. But what is the difference between those two disorders is the standard deviation. You see there is a factor 1/2 here. And that is what, it's very non-trivial, and that's what is going to create an Anderson, a topological transition driven by disorder. So this is basically the phase diagram. If there is zero disorder, here this is an axis for disorder. At zero disorder, my system is there. It's in a trivial regime. There is no topological invariant that is non-zero. If you increase the disorder, you follow this path, and it turns out, and we have shown this in this paper, that if you increase sufficiently the disorder, you are going to cross a transition where you enter a new phase that is a topological phase for some level of disorder, and regardless of this random number, site dependent. You have a range of disorder in which you will have edge modes that you can use. So let's see how it goes. I take a finite system as I send some wave from the left, and I look at the transmission. So if there's no disorder, this is a trivial insulator. So I see some Bloch modes, Bloch resonances, and a band gap. And what I want is a peak here. What I want is this transfer function. It doesn't exist without disorder. So my output is very far from what I want to do on my signal. The input is just a Gaussian signal. When I increase disorder, what happens is I'm closing little by little this band gap. This is a particular realization. And then the band gap closes and it's going to create my peak, the blue peak that I want, little by little. And when I get to the range of disorder, where this is a topological insulator, I get exactly the response in time that I want. So this is just one realization of disorder. Does it work on average? Does it work for all possible realization of disorder in that range? So to see this, we have done an average over 100 disorder realization of the spectrum. That's what we see. So here you have the frequency, you have your spectrum along that axis. And this is disorder. And we average the spectrum. And we see that indeed between two values, D1 and D2 of disorder strength, on average, you do have your Lorentzian peak. So that's exactly what we wanted to demonstrate. We have a system that doesn't perform any operation, any filtering operation. We move things around with a certain law, but still this is randomly chosen geometries. And all of a sudden it performs a precise, definite filtering operation. So we did the experiment with this. This is the ordered system. That it's very simple. And we indeed confirmed this peak. So this is also averaged over disorder realization. And we saw that we were indeed implementing that transfer function. We had this pulse at the output. So this is all good. And what we also did is, because we are working with time signals here, we were thinking that we might use this for robust disorder-induced image decoding. So what we do is we take an image of the Eiffel Tower, we transform it to a 1D time signal by going line by line in time. Okay, the higher the pulse, the higher the intensity of the pixel. We multiply this by the inverse Fourier transform of that Lorentzian, and we have an image that is encoded. And now we send this time signal through our system. And of course, if the system is perfectly ordered, we don't see anything at the output. But if we start putting some disorder to the system, we start seeing that Eiffel Tower image. As we close the band gap and open it again with the topological peak, we can decode the image. And this is non-trivial because you have to put the difference in the standard deviation, the hoppings, to get that image. We have done also some edge detection with this scheme that I don't show here. All right, so this brings me to my last part, and I don't have much time left, so I will try to do it a little bit faster. So this is about, can we use topology to manipulate energy? So we have goals, I will show you in a moment, which is, can we focus energy somewhere in space? Can we concentrate energy along the edge of a topological insulator? So let me summarize these goals. The first one is, let's say we have a 2D system where there's some, okay, it's some kind of metamaterial, and there's locations, let's say the corners, where I want to harvest the energy. I want all the energy to go there in order to use it. Let's imagine that I have a source somewhere, and my source is delivering some power. What I want is that at the beginning, it loads the system with some energy, and when there is sufficient energy in the systems, the energy will flow automatically using topology to the nearest corner. So I want to harvest the energy at the nearest corner after we have a sufficient level of energy in the system. So there's some kind of nonlinear thing going on. I want a power threshold after which we have this phenomenon to occur, that occurs. The second goal is a little bit different. is, okay, we have all these systems with edge modes. Okay, this is a topological insulator, or 2D topological insulator. But what I want for, if they have to be useful for something, I need to be able to focus energy to the edge mode, and a lot of energy. So I need to be able to couple a waveguide that brings a lot of energy very efficiently to match it to the edge mode. That's a very simple engineering problem. I want to tackle this one or two to see if it's possible. Okay, so let's see this first one. So for this, there is a concept that is very much useful. It's called second-order topological insulators. So let me just explain. As their name indicates, second-order topological insulators are different from first-order topological insulators. So let's see how. The first-order topological insulator is a system, here I take the example of a 2D system, that is gapped. So it has a gapped bulk. There is a frequency band where there is no mode. And inside that gap, I have my 1D edge states. So I have edge states inside the gap. The second-order topological insulator also has a gapped bulk. Inside that gap, there is also 1D edge modes. But the difference is that these 1D edge modes, they are themselves gapped. And in their gap, they also support edge modes, so corner states. So if you want, here, we can say that the side is itself a 1D topological insulator and has edge modes, which are 0D, so corner states. So the topology of the 2D bulk dictates the existence of these states. And that's what I want for my focusing at corners, because I want to have a way that energy can live there, so I can harvest it. All right, but because I said that I wanted to first load the system, and when there's sufficient energy, then it can be sucked to the corner, what I need is something nonlinear. So we proposed last year the concept of nonlinear second-order topological insulators. What it is it's a regular second-order topological insulator. Okay, for instance, this lattice with coupled hexagons in triangular lattice. But it's only a second-order topological insulator when I pump it hard enough. So when the intensity of the pump is low, I don't have any edge mode. It's not a topological insulator. It's just a normal insulator. There's no edge mode, no corner modes, nothing. However, if I start pumping more power to it, because I put some nonlinear hoppings inside the lattice, and this is well engineered, I can induce a phase that becomes topological with corner states. Okay? So without going too much to the details, let's look at the behavior. When the intensity, so low power, when the intensity is low, I have the linear behavior is a trivial insulator. I have a band gap, but there's nothing special to this band gap. Now, if I increase the intensity at some point, I'm going to close that band gap. Okay? And if I increase the intensity further, so I have even more power, the system reopens the band gap, but now becomes a second-order topological insulator. And we can do a topological theory of this. This is shown in this paper. Okay? So what happens is that after the threshold, so there is a closing of the band gap, and then there are two types of edge mode. There is the normal edge mode, which are themselves gapped, and then a corner states in the middle. So when I'm at low intensity, I just have a trivial band gap, but when I increase the intensity and I cross the threshold, in my band gap, I start seeing those corner and edge modes that appear. And if I increase further the intensity, I increase the size of the band gap. So these are more localized. We can see this here. If you have a low intensity, you are in the linear regime. This is a trivial insulator. All you see if you sweep frequency are a bunch of bulk modes. Now, if I increase the frequency and put myself in the topological phase, I see bulk modes. I also see edge modes, and I see corner states. And if I increase further the intensity, I just localize better those edge modes and those corner states. So we have validated this in experiments. So we wanted to build a platform that was easy enough so we can explore the physics, and we did that. So we have an electrical circuits with, let's say, couplings that are linear, those capacitors, and couplings that are nonlinear, those varactor diodes. And we excite it from a corner, and we look at the admittance, the electrical admittance here versus frequency. So if we send not a lot of power, let's say 0 dBm, that's the admittance spectrum we get. So we don't see clearly a band gap because the system is a little bit small, but we see a bunch of bulk resonances. What we know is that if there is a band gap, it's in the middle here, okay? And if I increase the power, I should see a big peak because there should be a corner states there. So the admittance should go very high. That's indeed what we see when we have a power of 25 dBm. These are simulations. I see a big peak right in the middle of my band gap. This is what I expect for the corner state. If I look at in space what I get, I do see something that's localized in the corner. And we have built this circuit. So this is a picture of the sample. And we have done exactly the experiment and found the spectra to be very similar. We have also mapped the near field at the top, and we see the same thing as in simulation. So, okay. So this brings me to the last part of the talk. I have shown how we can try to manage energy by using nonlinear topological insulators, and nonlinearities can drive topological transitions. Now, I go back to this engineering problem that I want is to match a waveguide to the edge, to an edge state, to a topological edge state. And this is not an easy problem. Why do I want to do that? Because if I want to use those edge states, I need to have an efficient coupling mechanism from the outside, either to put energy in it or to let the energy go. So the idea that we have explored is the use of a phenomenon that is known in the field of metamaterials that is called supercoupling via a zero-index medium. This was initially proposed by Nader and Guetta, Mario Silveria and Andrea Alu in electromagnetism. And in this paper, back in the days where I was a student in Texas, we proposed the acoustic equivalent. So basically what we have is we have a waveguide, and we can match this waveguide, it's really impedance matching, to a channel that is very narrow at the condition that the refractive index in the channel is near zero. Okay? So then a wave comes here and goes through the channel without a phase difference. And this near zero index of refraction was built using resonant membranes at that time. So what I'm going to show you is that we can have the same type of phenomenon at the edge using an edge mode. So this channel in the middle is going to be the edge of a topological insulator. But we need an edge mode with zero index of refraction or an infinite phase velocity. So without going to the details, it happens in some special 3D topological insulators that have wide points. So you can show that if you take a simple cubic lattice with some degrees of freedom, sufficient number of degrees of freedom in the hoppings in different directions, you can have wide points. And by changing the value, by tuning these hopping values, you can tilt the band structure, making a so-called type 2 wide semi-metal where the wide points are tilted. And at the transition between type 1 and type 2, you have something that is flat like this, reminiscent of flat bands of zero index kind of things, or zero group velocity kind of things. So infinite phase velocity kind of things. But this is the bulk band structure. What about the edge modes? Well, what is fascinating about this situation is that the edge modes also inherit the zero index behavior in one particular direction, the direction of that can be picked as the edge of the sample. So it's very interesting. And here I don't go through details too much, but if you pick the parameters right and the direction right of the edge mode, I mean, you can have an edge mode that is completely flat in one direction. It's not flat in other direction, but in the direction of the edge, it's flat. If you cut the edge in the right direction, it can be flat. Okay? So it's very interesting to try to use this for supercoupling, and that's exactly what we did. So we built this semi-metal, and we did the same experiment as we did for the zero-index metamaterials. We have a waveguide, another waveguide, we have the sample and the edge of the sample, and we tried to couple this. And indeed, we could measure the near zero phase delay through the channel, and we could see a resonance transmission peak. So if you look at what happens is basically you have your wave coming in, it couples to the edge mode. This is kind of a quasi-static edge mode, and you leave to the other side here with full transmission. So you can really couple all the energy with a little bit of reflection because it's difficult to tune, but you can do it at least in. I mean, if you tune the width of that waveguide, you need to tune the impedance of that waveguide to this one. So you need to tune that width to show this phenomenon. All right, so this brings me to my conclusions, and I presented, I would say, a different aspect of topological metamaterials. We have focused a lot in 1D scenarios to try to go from physics-driven explorations to more engineering-oriented applications. And we have asked questions like, can we do filters? Are they robust? Can we do disorder-induced filters? Do we care about disorder that much? What type of disorder are we robust to? And we have shown also that in order to manipulate energy, there are some opportunities. So we didn't quite demonstrate the energy harvesting yet, but that's our vision. And we have shown that we can certainly try to play some tricks that we know from metamaterials to match system or to couple efficiently energy from the outside to these edge modes. So I want to acknowledge my student Farzad Zangane, who basically did most of the work that I presented, and also my postdoc Nadesh Kaina, who worked also on these definitions of topological invariants in her Marie Curie fellowship. So thank you very much, and I'm open for any questions you may have.
So thank you very much, Romain. Very exciting talk, actually. I guess there will be lots of questions on every part. So let's start perhaps with part one.